Welcome to our first lecture on group theory. For those already familiar with rings and fields, like this audience here, breaking into group theory is actually easy. Groups are, to some extent, very similar to the other objects, like rings and fields and vector spaces. So let's look at the definition. So just like in the case of rings and fields, you start with a set. And I suggestively denote this set by G, G as a group. So a group is a set together with a binary operation. Now, the first difference, before I get into any other differences, is that there's only one binary operation now. So in case of rings and fields, there were always two operations called addition and multiplication. In the case of vector spaces, there were also two operations, addition of vectors and scalar multiplication. Here there's only one operation. And I denote this operation by star. Sometimes this star will be addition, sometimes this star will be multiplication, sometimes this star will be something completely different. So for now, I'm going to use star for the operation. And sometimes, especially when we get far enough into the theory, I'm just going to drop this altogether, and just whenever I write two elements next to each other, we're just going to assume that I mean to apply binary operation to these two elements. But for now, I'm going to use star. Okay, and this operation star satisfies three properties, none of them unfamiliar to you. First one is associativity. The second one is existence of an element, neutral element, that doesn't do anything. That element would be called the identity, right? So E would be the identity. So identity is an element such that G times E, I'm saying times, but remember, it doesn't have to be multiplication. So G star E is equal to E star G is equal to G for all elements G and G. And finally, every element in a group has an inverse. So for every G and G, there exists some element H such that G star H is equal to H star G is equal to E. So that H is called the inverse, or at this point just an inverse of G. We don't yet know that inverses are unique, but you might expect they actually are. So I'm going to write G inverse for H, but this sort of notation already assumes that inverses are unique. So, but we still need to check that inverses are unique. And I'll leave this as an exercise. How do you show that inverse is unique? Well, first of all, you'd like to actually show that identities are unique, so they're also unique. How do you show that something is unique? Usually you just assume that there are two such things, and then you show that they're actually equal. You've done such proofs when we studied ring theory. They're no different here. In fact, perhaps maybe even easier for groups. So the uniqueness is not part of the definition, but in order for me to introduce some nice notation already, like writing G inverse rather than just H, I'd like to know that inverses are unique. So the definition doesn't say anything about uniqueness, but then you prove these two little facts, and in fact, inverses are unique. Unlike the addition and multiplication in rings, the binary operation in groups doesn't need to be commutative. But if it is, so if G1 star G2 is equal to G star G1 for all elements G1 and G2, we call G abelian. Why don't we call it commutative? That's for historical reasons. This terminology here comes from the Norwegian mathematician Abel, sort of one of the pioneers of group theory. So in case of groups, whenever we have a commutative group, we just call it abelian. And finally, let me define right away what a subgroup is. So if I take a subset of my group G, I call it a subgroup provided that it's also a group. And it's not just any odd group, it's a group with the same operation that I had on G. So G came with some operation star, and sometimes I might write G comma star to sort of to emphasize both the set and the operation. Mostly I'm not going to do it. When I say let G be a group, I already assume that G is both a set and there is an accompanying operation with it. But sometimes I will do that, and you'll see a moment in examples. So if I have a subset of a group, if it's also a group with respect to the same operation. So in particular, if it's in particular closed under that operation, if I take any two elements of H and I star them as elements of G, I better get back an element of H. Also, the identity in G is the same as the identity in H. So in particular, the identity in G lives in H. And then every element of H, because it's an element of G, it has an inverse in G, but the inverse must lie in H. And then such an H is called a subgroup of G. And the notation is like this, looks like H less than G. This also includes the possibility that H and G are equal. There's always this ambiguity in mathematical notation that maybe I should put a little bar underneath here to emphasize that I'm also allowing equality. However, I don't want to do it. According to the definition, this also allows for H to be G. And in fact, we always have these very two trivial examples of subgroups. So if somebody asks you on the test, gives you a group and say, write one example of a subgroup of that group, that's actually a very easy question, because there are always two examples for any group, almost any group. Two trivial examples of subgroups, namely, the entire group is, of course, a subgroup of itself, because it is a subset and it is a group, under, of course, the same operation. And then if I just take the identity, the set consisting of just one element, namely the identity, that is also a group. You see, so if there's only one element, this thing just checks out because it checks out for any elements of G. So in particular, if every one of these elements is equal to the identity, this is true. Then there has to be identity in this set, but that identity is just this identity. And then every element must have an inverse, but you can just check that an inverse to this identity is the identity back. So just the one element consisting of identity is a subgroup. No other singleton, no other one element set would be a subgroup, because there always has to be the identity inside any group. So if a subset is H is supposed to be a subgroup, it must have identity. So this element must always be inside H. So if you want a one element subgroup, that's the only option. Why did I say it's almost always true that there are two subgroups for any given group? There's one case when that isn't true, and namely when the group G itself is just this one element. Then of course G and this element are the same subgroup. So then there's only one. Okay? So, and a group consisting of just the identity of one element equal to the identity is called a trivial group. Okay, so if I take a set with just one element, there's only one structure of a group I can put on this set. Namely, I have to make this one element the identity, because identity must be in any group. And that is already a group. It's a particular example of a group. The smallest group there could be just one element group. And I'd call it trivial group. Okay, so let's right away get into examples. Because as I just said, one advantage of having already studied rings and fields is that we have an abundance of examples of groups. You might say, well, how do I now want to use rings and fields as examples of groups? Group is only allowed to have one operation, and rings and fields have two operations. So does that mean that no ring or field can be considered as a group? Well, I mean, let me just give you this analogy. If a dog owner is someone who owns a dog, does that mean that a person who owns two dogs is not a dog owner? Yes, they are. And in fact, fields and rings are also examples of groups. It's just that we're going to restrict to just one operation. So let's begin with the following example that this is almost our primary example for almost everything. So I'm going to write G, Z, and the operation star will be the addition, usual addition in Z. So is Z with the usual addition a group? Let's see. Addition is certainly a binary operation on Z that is associative. There is the identity, namely the zero in Z. And does every element have an inverse? Remember, the operation here is addition, so the inverses are just the negatives. So yes. Okay, I'm going to write something like this. So for every n, and this notation is somewhat confusing because this usually was reserved for multiplicative inverse. Right now I'm using it for the inverse inside a group. And this sort of notation will cause complications for us. So we will allow ourselves some flexibility in notation that I will explain a little later. But for now, this looks cumbersome, but what that means is the inverse of n under the star operation is the negative of n. So G is a group. So Z is a group. So Z with the operation plus is a group. Okay? Remember, group consists of two elements, a set and an operation. So I'm just going to separate them here by a comma. Let's move on. Another example, 2. What if I take rationals? And again, I take star to be addition. Usual addition. In Q. Well, let's quickly run through the axioms. Is it associative? Yep. Is there an identity? Yes. What's the identity with respect to addition in Q? That's the 0. And what about the inverses? Well, same as for, maybe I should use n, I don't know. A maybe. Same as for the integers. Note that I'm completely ignoring multiplication in those rings. But if you look at these two examples, then you see there's nothing specific I'm using about Z or Q. Really, what I am using here is operation addition, which exists in every ring. Then I'm saying that the operation has to be associative, as addition in every ring is. Then I'm saying the identity is the 0 for that addition. That also exists in every ring. And finally, that every element has an additive inverse, and that's again true for every ring. So if I take any ring and just look at the addition operation, I got myself a group. So because you know so many rings, you already know at least as many groups. So this is sort of the third example, covers already a lot of cases, infinitely many in fact. If R is a ring, so I'm going to do it this way, okay? I'm going to write the addition and the multiplication here. So R is a ring, I usually just write it this way, but now I just want to stress that there are these two operations, addition and multiplication in a ring. Then, if I just take R with addition, so I forget about the multiplication, then this is a group. All right? So star is addition. The identity is 0 in R, and the inverse is just a negative. Again, this for the moment does not mean the multiplicative inverse. This just means the inverse in the group, in this group under the operation, which in this case is addition. So you now have infinitely many examples of groups. And let's just look at some other things we defined a moment ago. We said if a group is commutative, then it's abelian. Now, is this group commutative? Are the integers with addition commutative? Yes, they are, right? Addition in the integers is commutative, so this is an abelian group. What about Q with plus? Sure, same thing, yes? And what about any ring? Addition in any ring, is it commutative? That's one of the axioms of an addition in a ring, so yes. So this is also abelian. So we have now infinitely many examples of groups. Secondly, note that, so here, note, the integers with addition are a subgroup of the rationals with addition. Yes, integers are certainly a subset of Q, and if I add two integers as rational numbers, that's the same as adding them as integers. So it's a subgroup. So because of 3, right? Because of 3, you have many examples of groups now. So sort of from this, we get many examples. For example, Z mod NZ with addition is a group. In fact, abelian group. What else? So maybe I shouldn't use R. Maybe let's use F. Fx with addition of polynomials. So let's say F here will be, it could actually be any ring. It doesn't have to be a field, right? It could be any ring. So this is also an abelian group. Whenever you start with a ring, you have a ring, you can just use addition and form yourself a group. Okay, but rings come with two operations. So maybe I can now use the other operation, sort of forget about addition and just use multiplication, and also get a group. Let's examine this. Example 4. I'm going to take G to be Q and star to be multiplication, usual multiplication in Q. So let's quickly go through the axioms. Is this multiplication in the rationals associative? Yep. Is there an identity for multiplication in the rationals? Yes, that's 1. So E would be 1. Remember, now the operation is multiplication. Does every rational have an inverse under multiplication? No. Okay, so here it breaks down. there's just exactly one rational which doesn't have an inverse on the multiplication, that's 0. So 0 has no inverse. So Q together with multiplication is not a group. G with the usual multiplication. I can define multiplication on Q with usual multiplication. I can define multiplication on Q to make it a group. But with the usual multiplication, it is not a group. But the only problem seemed to have been the fact that 0 didn't have an inverse. So what if I throw it out? So 5, or actually 4 prime. 4 prime. G rationals but without 0. And star usual multiplication. Okay. Associative, sure. And you have to just make sure, that this operation, that this thing is actually closed under the operation. So in other words, that multiplication defines a binary operation on non-zero rationals. In other words, if I take two non-zero rationals and I multiply them as rationals, that I get a non-zero rational. But, Q is a field, so it's a domain. So two non-zero rationals, when I multiply them, cannot give you 0. So yes, if I take two non-zero rationals and I multiply them, I get a non-zero rational. So the multiplication on rationals defines a binary operation on this G, on the non-zero rationals. Associative, sure, because look, you're really reaping the benefits from proving all these things for rings and fields. You already know that multiplication in any ring is associative. So you don't have to check this, right? You know it's a multiplication in the rationals is associative. Is there an identity? Yeah, well, this, right? It's still the same thing. And does every non-zero rational have an inverse on the multiplication? Sure. So that is a group. Q without 0 is a group. Abelian? Yep. Abelian group. All right, let's try the same thing with the integers. Oh, I already know that 0 couldn't possibly work. So I take integers but without 0. Oops, usual multiplication. Associative? Yeah, integers are a ring, so multiplication is associative. Is that still the case that this defines a binary operation? So if I take two non-zero integers and I multiply them, do I get a non-zero integer? Sure, integers are a domain, so again the same thing holds. So it is a binary operation. It's associative. Is there an identity? 1 is the identity. Does every non-zero integer have an inverse? No, right? In fact, there are only two integers. As you know by now very well, there are only two integers that have inverses, multiplicative inverses, and that's plus and minus 1. So no inverses, right? So any integer other than plus or minus 1 has no inverse. So Z without 0 with multiplication is not a group. So it went really easily with addition. If you give yourself a ring and then you take the addition, that easily defines a group. With multiplication, there seem to be problems. First, it looked like 0 was the problem, so we removed it and we made Q without 0 a group. Then we removed 0 from Z, and that somehow isn't enough. Because not every element in Z, other than 0, even other than 0, has an inverse. But we actually know already even a name for a subset of a ring in which every element is invertible, right? Such elements that have multiplicative inverses are called units. So what are the units in Z? So if I take, units in Z are just plus and minus 1. Is this a group? So let's see. So if the star here is multiplication, usual multiplication in Z, is there the identity? Yep. Does every element inside the units have an inverse? By definition, right? Units are elements that have inverses. So this is a group. So plus 1 and minus 1 together with multiplication is a group. Abelian group again. But the notion of a unit is not specific to Z. It's completely general and can be defined for any ring, as you know very well. Note, in particular, this thing was also exactly units in Q. So we can talk about a general example. This was units, not very good erasing, in Q. So we have this general statement, right? So 6, if R is a ring, and actually let's again emphasize the operations in R, plus and times is a ring, then the set of units in R together with the operation multiplication in R is a group. And in fact, this group has a special notation, R cross. And I could write comma dot, but this notation already subsumes that into it. So when I write R cross, I already mean the set of units inside the ring R together with the binary operation that is the multiplication in R. For us, remember, all rings were commutative, which meant multiplication was commutative. So this is actually an abelian group. It is an abelian group. Okay, in the next video we'll do more examples.